Hello, everybody. Hello and welcome. Thank you for joining us today. I will start the presentation straight away. My name is Paul Marley. I'm the Technical Training Manager for HYDAC in Australia. This is episode 11 of an 11-part series, the Oil Filtration webinar series. And the subject of today is filter sizing calculations. We've got a poll at the start of this. You'll find that in the poll tab on the right-hand side. And then at the end of the session, of course, we'll have an opportunity for some questions and we'll address that. So without any further delay, let us get going. Thank you for those that are joining us again. We've had some regular visitors, so it's a pleasure that you're following along here. So this is the last episode where we're looking at finding solutions. So filter sizing calculations is what this one's about. Last week we addressed how we select the filter media. I'll ask a question here. We'll come back to this at the end. I learned to select the correct fluid filter through calculations we've got a few choices there. I am interested as a trainer in knowing whether or not this is being taught in our technical colleges. I would like to think it is, but it may be something new to you. So whether you're going to TAFE in Australia or a polytechnic somewhere else around the world, are you learning that in formal education? Or are you learning that in the field? So please click on the poll as we go. Okay, so let's keep going. So part one, how we select the correct filtration solution. We did part one of this last week, and the solution is something that we're going to find with a few inputs and a few variables. There's some things that we have to address. Just as a revision, the location of the filter, the function of the filter, the form of it. So the three of them together are really the what it is. The media, and that was the subject of last week's webinar. The media is the type of filtration rating that we have in the element. The size of the filter is related to the media, and the indicator is really the last thing we choose to supplement that selection. So again, today we're looking at the size and how we come up with the correct solution for the size of the filter. Now, how we size is on a delta P value. So the delta P value is the pressure differential, and it's defined as the clean element pressure drop, or delta P. That is the initial pressure drop across a new element. So a new element that is clean, it hasn't collected any contamination yet. You get this new element, you fit it into the filter, up or down, and what is its pressure differential across the filter? We're sizing on that. We're not sizing on port size. We're not sizing on physical dimensions. We are looking at the clean element pressure differential. And that's not necessarily something that is going to come to mind first. So I want to describe why that is and why it's so important to us. Okay, so just for clarity, of course, the differential pressure across the filter is the difference between the pressure before the filter element and after the filter element. That is the delta P. And it's something we read as we have flow across an element. So the reason why it's important, ultimately, we need to know when we need to change the filter. And to do that, we need feedback, and the feedback mechanism is very often a filter indicator, as shown on the left-hand side of the screen. So the filter indicator then is something that will usually say green is good, red is bad. And of course, caution, you might get an amber in between to say it's time to change your element. So here's our indicator here. Now, on a standard filter, I will say a pressure type filter, in the HYDAC range, this is a 5-bar setting. Now, so when we start off using our filter, we have a low initial pressure differential across the element, and the indicator is showing green. It's not indicating. As we use the filter, we're catching contamination. What's going to happen then is the filter differential pressure will increase over time, and it will keep increasing, and it does so slowly, and then it will actually increase in how quickly the pressure rises. Okay, this is how all filters are going to work. As the pressure differential rises, we get to a point of indication, and that's going to tell us to change the element. And if we don't change the element, we're going to get into a filter bypass condition. So that's 5-bar indication, 6-bar bypass on a standard pressure range. Now, the reason why the delta P is so important to us is because of service life. If you have a low initial delta P, as low as possible, then you have the maximum operating hours from the time you fit the element to the time it needs replacing. So say, for example, this is showing that we have 1 bar on this graph, 1 bar out of 5 where the indicator is, 1 bar clean initial pressure drop and a 5-bar indicator and a 6-bar bypass gives us operating hours of whatever. It depends, of course, on the cleanliness of the system and the contaminants it's removing. If we started at 2 bar, for example, you can see what it's done to the operating hours. So that's why the filter pressure differential is so important to us. It's about getting the optimum size, have the optimum extended life of the element. Okay. Now, if we start with as low a pressure differential as possible, then it will give us the most cost-effective filter action and the most cost-effective removal of contaminants, and that will leave us with the best outcome with regards to reliability. Okay, so really the target then very often is a 1 bar pressure differential on a 5-bar indication. Now, where that's discussed is in the catalogue, and I'll show you that in a moment. But where the filter is located will change that target delta P. So for offline filtration, it's not a percentage of the indicator, it's a finite pressure. So 0.15 to 0.2 bar is a clean target. For a suction filtration, 0.04 bar is our target, and more commonly, or very commonly, we're going to see pressure and return filtration. They share a value with a bypass in your filter, 0.15 to 0.2 times the indicator pressure. So that is 15% to 20% of the indicator pressure is our clean target differential. If there's no bypass fitted in the filter, then 0.15 to 0.2 bar. Okay, so that's basically then the same as an offline target. Okay, so as a rule of thumb, for very common return and pressure filtration, 15 to 20% of the indicator value. So this is all described in page 28 of the current HYDAC catalogue, and of course it is in our filter handbook as well with the same information. But you can see there then that same information is then displayed as a table. Okay, so that's what it's all about, and that's why we're choosing a filter based on clean delta P target. Okay, so let's look at the calculations that we're doing. Ultimately, if we are looking at a delta P, then that will be affected by the following factors: the physical size of the filter, the element, and its matching housing. If you go for a smaller filter, you increase the delta P across it. The flow rate of the fluid. If you increase the flow rate, you increase the delta P across it. The viscosity of the fluid. If the fluid viscosity increases, that's the thickness of the fluid, then the delta P will increase. The density of the fluid. So if you have a heavier fluid, then the delta P will increase as well. And finally, of course, the subject of last week's webinar was the media of the element. So the tighter the mesh pack on that element, the better dirt removal it has, but you increase the delta P as a consequence of that. So all of these things are important to us. So a change in any of these factors will change the delta P total. And as a consequence of that, we can't size a filter adequately and correctly without knowing all of these. You have to understand the system to make a decision. The subject of this webinar is, of course, the physical size of the filter. I want to describe how that is used in our calculations. So the first calculation is this, and it's simply addition. The total delta P across the filter is the delta P of the element plus the delta P of the housing, okay, because, of course, the element's inside the housing. Now, the element will have the highest pressure drop across it. The housing is very open, really. It's a series of ports and basically a bowl if you have fluid flowing through something without media. So It can't be disregarded, though. It cannot be ignored. The two of them together have to be evaluated because they will be used together. So we'll start with the housing pressure drop. How we find that is we look in the catalogue, and for each filtration product, there will be a graph such as this. This is pressure differential on the y-axis and flow rate on the x-axis. So as flow rate increases, so does the delta P across the filter. Now, it's important to understand that this doesn't include taking into account a change in viscosity, which of course it will increase the delta P of the housing. So the delta P of the housing, looking at the graph, say for example 73 litres a minute flow rate, you can see that on this particular size, it's a DF60 or 110 or 140. They are the same filter, I will say, same filter head with a longer bowl. And evaluating the length of the bowl doesn't change anything. So it's really the pressure differential of the head. They share a common head. So 73 litres a minute, 0.35 bar pressure differential. We then have to take into account our correction of our viscosity because the charts in the catalogue are all rated at 30 centistokes. So that is 30 millimeters squared per second. That's the viscosity of the fluid. And it's also with a mineral oil. So the the density correction and the viscosity correction are important to us. You throw all that together and you end up with the total housing pressure differential. Pretty easy, pretty straightforward. The element then is a little bit more complicated, but not much. So what we've got then is the delta P of the element equals this. It is the flow rate multiplied by the element gradient coefficient over 1000 multiplied by the operating viscosity over 30 multiplied by the fluid density over 0.86. So let me describe all that. The flow rate is, of course, going to be in common flow rate terms, that is litres per minute. So, of course, that will change the delta P of the element. The size of the element physically is taken into account there, as is the media, and I'll come back to that. The operating viscosity is over 30, and the reason for that is all of the data in the catalogue and the way the tests have been done and the way the information has been presented in the catalogues is at 30 centistokes. So you have to take into account a fluid viscosity change because you will most likely not be at 30 centistokes. So the viscosity correction is done by putting the operating viscosity above 30. And where do you find the operating viscosity? Well, basically with your fluid data sheets. So you talk to your fluid manufacturer or supplier, and of course they'll be able to give you viscosity information on that fluid. The density is pretty simple to apply. Basically, the most common use for these filters is with mineral oil. If your oil is not a mineral oil, of course, it'll have a different density to 0.86 kilograms per cubic meter. So that is the fluid density and how we take that into account. Okay, coming back to this little area here, the element gradient coefficient over 1000. What is that? Well, again, that's where we take into account both the media and the size. So this is basically a gradient. And this is something that the HYDAC team, the filtration team, are going to publish on these elements. Every element they will give you a figure because you can't size a filter adequately without this figure, and you can't actually evaluate filter performance without testing it. Okay, so the element graph is determined according to ISO 3968 and always corresponds to a straight line with a specific gradient coefficient, and they name it SK in the global catalogue for HYDAC. The catalogue for the USA, it's applied a little bit differently. They don't call it an SK, but it is the same thing. So this represents the ratio of the flow rate to the pressure drop for a clean element. So it's pressure drop in millibar over flow in litres per minute. So it's millibar over litres per minute, and it's basically a rise over run, x over y over x. It's described as a gradient, and it is a coefficient. It is a number. So the SK gradient can be found in the catalog data sheets for the elements. So if you can't see it in your catalog, you're probably not looking at the element part of the catalog, okay? But you're looking at the housing. Housing pressure drop data is with the housing, and the element pressure drop data is with the element. So you can see here then, this is for a pressure element, a Druch element, optimicron type. As an example, we have sizes from 30 up to 1500, and we have media then from 1, 3, 5, 10, 15, and 20 micron. And you can see that the smaller the filter is with a more tight media, the number will be higher than if you go for a larger filter. As we go down the page here, you can see how the number gets smaller. Same again with the media. If we go across the page here, we open up the media from 1 to 3 to 5 micron, you see the number gets smaller. So of course, the larger the filter, the more open the media, the lower the SK gradient. Okay, I'll just go back 2 steps. In the United States catalog, which is slightly different, they give you a coefficient, but they don't do it over 1,000. They simply just multiply the number out and don't make it over 1,000. But that's the way it is. But in the global catalog, it's over 1,000. That's the background to what we're doing. Let's look at how we calculate. Okay, so I am just using as an example here. We're not going to go into this in a lot of depth. This is an overview into how it works. I have just simply got, written on a Post-it note, some figures here. So we know the fluid. This will be an ISO VG 46. And we know then at 10 degrees will be 270 centistokes, at 40 degrees, 46 centistokes, and at 60 degrees, 21 centistokes, because we know the fluid data from the manufacturer. We know our flow rate will be 73 litres a minute. And we've already done what we talked about in the last webinar, and that is that we've selected our media to meet a target cleanliness level. So we've selected 3 micron media. Due to the fact of the element being the filter and the product being what it is, this is a high pressure filter. It will have a bypass of 6 bar and an indicator setting of 5 bar, standard for these types of filters. And the target differential delta P clean target is 1 bar, okay, which is 0.2 of our 5 bar indicator setting. Okay, so that's what we're going to look for. So 73 litres a minute. Now, we have to choose a filter first because we have to look up what the SK gradient is. And to do that, we have to choose a size. So I'm going to choose a size and go, yeah, 110. Now, this is a guesstimate. Now, we're saying, okay, maximum flow rate, 73 litres a minute, 110. If that is flow rate, then it'll be more than that, and it should suffice. Let's go. Now, this filter, by the way, will have a 3/4 inch thread. Now, with this filter, we can look up the delta P flow gradient coefficient for it. Of course, this is a 110 size and a 3 micron element. So you can see here from the catalog, this is going to tell us that the SK gradient is 13.4. Okay. Be aware, though, we have to look at the type of filter it is. This is a pressure filter. This is a pressure filter element. Okay. Make sure you get that right if you're looking it up in the catalog. And then we throw these figures into that little equation. So the delta P of the element equals 73 litres a minute by 13.4, that's our SK gradient, over 46, this is at 40 degrees, 46 centistokes. And then the density is 0.86, this is a mineral oil. So we get these figures and we calculate that out to a total of 2.03 bar. Straightforward. It's basically division, multiplication, and addition. Now, that gives us our number, 2.03 bar. That looks pretty good. We haven't reached our target, but you might say, and you could commonly say, well, the target's 1 bar, this is 2 bar. I do hydraulics, 1 bar isn't much, 1 bar isn't important. Let me show you why it is important in this little exercise that we're doing. Now, That was at 40 degrees. If we're operating, say, at 60 degrees, that's a typical operating temperature here. Now, I just wanted to highlight here, each of these factors that I talked about before, I've highlighted in red, okay? Now, one of these has changed now because we've gone from 40 degrees, which is where we're 46 centistoke, to 21 centistoke because we've gone to 60 degrees. So I'm highlighting the 4 factors plus the one that has changed. So in our calculation, this 0.7 is different. So that then is how this is going to add up then to 0.925 bar. So you can say, okay, look, that works because at operating temperature, we've reached our target differential. And that would be, in many cases, adequate. But the question you have to ask is, what will happen when this fluid is cold? Because if it is running and it's cold, we have to take into account the worst case scenario, and that will be that. So looking at a cold start situation, 10 degrees Celsius. So our viscosity is now around about 270 centistokes. So that's multiplied then out to 11.95 bar. 11.95 bar, you won't actually get there. You'll be in bypass at 6, but you can see that that is not a good solution. You are not filtering at all when you start the machine. So that could lead to problems with regards to your cleanliness. Now, also, if it's a machine that doesn't run often, this won't work because it won't warm up to a point where you're not bypassing. So you can see here then that the target's very important to us. So I would suggest that 110 isn't the right size. We want to now go up to another filter. Now, I could just jump up to the next one up, which is a size 140, or I could choose to jump a few. I will do that for the sake of expedience. If we selected then a DF 240, we'll move a little chart along there. A DF240 is the same type of product. It's larger. It's now a 1 3/4 BSP thread. Okay, so let's apply that. Now, what's changed now? We've still got our worst case scenario is 10 degrees. This remains the same, but then I've changed then our filter size. So the filter size changes the SK gradient, changes that little number, and changes our total number that we find the pressure differential total. So we're now at 5 bar. Now, if we look at this, we are at the indicator setting. So on a cold start, we're not bypassing, we're indicating, just starting to indicate. And things will only improve as the system warms up. So I've then looked at the same information again, but at an operating temperature. I've just chosen here 50 degrees now. So what that will change now is the viscosity. So the same calculation with the same figures has a 30 centistoke oil, which is just by chance the same that's in the catalogue. So this brings this down to a 1. We now have a total delta P clean element differential of 0.56 bar, well under our target of 1 bar. So I would suggest this indicator is below our target. We could choose one that is 1 bar, but we would most likely be bypassing at a cold start. Just hitting your indicator is, to me, a nice solution, one that will work very adequately in the field. Now, how do you add all these things up? Well, it's pretty straightforward. You can do it with a calculator. Just a bit of a tip. I've grabbed a screenshot here on the right. I tend to use a web-based calculator. And the reason I like that one is because I can lay it out, the calculation, as shown here. So if I go to change, for example, the viscosity, then I will change it here and here and here, and it just adds up all of this anyway. So I don't have to put the whole calculation in every time. Okay, so there's a few web calculators that will do that for you. You could do it in Excel, of course, as well. So I would suggest then looking at the solution we've got, a 240 size would do the job very neatly. It will give us the target cleanliness that we're looking for because it's a 3 micron media. We've looked at that last time. It's the correct size for what we're trying to do. It won't be in bypass. We won't be changing it too often. This will be a perfect solution and one that ticks all the boxes. So that, ladies and gentlemen, is how we do it. Now, we actually don't use Excel here in HYDAC World. We actually use computer software. Now, that software is available to you for free on the HYDAC website and in the HYDAC Tools app. So it's called Filter It 2. And you can see here what I've done is I've put the same data in as we had with the manual calculation. So I had 0.56 bar as my total pressure drop. The software gives us 0.52 bar. So very, very accurate. Doesn't make any difference if you do it manually or, of course, using the software. But the software, of course, will give you some lovely graphs as to how this actually works, and it's easy. So that's we size with software, but you might ask the question, well, why have you gone to the trouble then, Paul, of giving us all this stuff about calculations, and why have you made it so difficult? The reason is covered in the summary. We are targeting a cleanliness outcome. Okay, so ultimately, we have to remember we have a job to do, and we choose the media based on what we want our system to do and what we're trying to protect. That's why we choose filters. We use a clean element pressure drop target to size a solution with a long service life, because we have to remember that's another outcome as well, is having the maximum operating hours. That is value for money. So value for money, good filtration. And we need to understand the application, okay? So again, the physical size of the filter and the media, the flow rate, the viscosity, the density, all of these things lead to a change in the delta P. So the reason I've taken you through all of this stuff about the calculations, the manual calculations, is for a few reasons. Number one, if you know what that calculation is about, then you understand that every decision you make, every change the system has, affects the outcome. And changing the outcome changes everything, because you want an outcome that works. Okay? So you, in understanding the calculations, you understand the importance of these things. You understand that understanding the application is important. And secondly, if we know how to do the manual calculations, then if the website goes down or an asteroid hits the planet and we can't access the HYDAC website, there's always the catalog, and you can solve it without electricity. Number three is, if you then understand the calculation, then you understand really what the software is asking you and why it will start, for example, as a default with a 1 bar differential. Okay, if you understand what the calculations are, you understand what you're doing, because the calculations reveal the science behind the engineering. Okay, so again, it's about choosing the right solution, one that works well, and one that leads to reliability. Filtration is important. Filtration is one of the most important parts of lubrication and hydraulics. So that brings us to the end of our oil filtration webinar series. We've ticked all these boxes. So it's been fun. We started this one at the end of July, and here we are at the end of the year. So it's nice to know that when you make a plan in 2020, things still can go to plan. So that's awesome. Thank you for everybody who's joined us along the journey. There will be future webinars, of course, in 2021. When and how, I don't care. Christmas comes first. We'll deal with the webinars in the new year. But of course, this has been a real joy to present. Okay, so that brings us to the end of our series. It's been an absolute joy. Thank you for those that have come along the journey from the beginning. Thank you for the feedback we've been getting as well on the comments on YouTube when these are posted. That's very encouraging for us, and we really appreciate it. If you found it handy, of course, we'd love your feedback over the total series of this oil filtration webinar series. So that brings us to the end. Everybody stay safe, have a fantastic Christmas, and we will see you shortly in the new year. Cheers.